Greetings! And welcome to this video tutorial of Danzig's Simplex Algorithm, a method for solving linear programming problems. Linear programming is used to calculate optimal solutions to problems that can be modelled by linear equations. Problems can be described in a standard form, using an objective function to be maximised, problem constraints, and non-negative variables. To solve linear programming problems, we can graphically represent the linear equations to obtain a feasible region, as seen on the graph on the right.
The shaded region in red is the feasible region.
The optimal solution for the problem will occur on some boundary of the feasible region, which in the graph is between the axis and the linear equations. The maximal value will occur at a vertex of the feasible region, where the lines intersect, marked here by the purple dot. However, graphically representing linear equations in more than 3 dimensions becomes difficult. For these problems, we have another, easier way to find the solution by using the simplex method.
The simplex algorithm, given an objective function z, attempts to maximize z, subject to a set of linear constraints. The algorithm requires the constraints to be in a standard form, which is the result of manipulating your equations to a form identical in mathematical meaning, yet notationally suited to run the simplex algorithm on. To convert them to a standard form, it is necessary to change equations to inequalities. You can introduce new variables, negate inequalities, change from minimization to maximization, or vice versa, with negation. Next, the objective function and inequalities are converted to slack form. We introduce slack variables to change the constraint to an equality constraint. The slack variable represents the difference between the two sides of the inequality and is assumed to be non-negative. On the left-hand side of our equations, we have our slack basic variables. On the right-hand side, we have non-basic variables. Visually, in 2D, the algorithm starts at the green point. Simplex asks whether we can increase z. It finds z can be increased by increasing x until we hit a constraint represented by the blue point. Any further, and the solution would be infeasible. Simplex then repeats this process for all other variables, such as y in the objective function. The solution will always rest at a vertex. We check the solution space is initially feasible by setting the non-basic variables to 0. We must ensure that all of our slack variables are non-negative. If any of them are, we perform the initialized simplex algorithm, which will not be discussed here, in order to arrive at an initial feasible solution. Once the starting point is feasible, we perform 0 or more pivot operations. A pivot operation involves selecting a non-basic variable with a positive coefficient in the objective function. Each iteration of the algorithm moves along an edge to a neighbouring vertex whose objective value is greater than the current vertex. In order to avoid a cyclic degeneracy where the pivoting operation continues infinitely, it is advised to use Bland's rule. I will not talk about that here. If all non-basic variables in the objective function have negative coefficients, then our solution is optimal. We stop the algorithm as the objective function cannot be further increased. The algorithm terminates at a vertex, which is a local optima. The vertex, however, is located within a convex hull, which implies that the local optima is in fact a global optima also. If it is not yet optimal, we select a non-basic variable with a positive coefficient from our objective function and attempt to maximize it in all of our inequalities. We maximize it by the greatest possible value without violating any constraint, i.e., we ensure all slack variables remain non-negative. A further note is that for a linear program, there exists the dual of the linear or primal program, which can also be solved to arrive at the same solution. I will not discuss that here. This method of choosing the maximum of the minimum equations to increase the selected non-basic variable by results in the identification of the first constraint that will be encountered. When this constraint is reached, its slack variable becomes 0. If there is no restricting constraint, then we can increase our objective function infinitely, which indicates the constraints are unbounded in at least one direction, and therefore simplex cannot solve it. We then pivot. Firstly, we swap the non-basic variable in the equation which had the smallest constraint with the basic variable. We then substitute this new basic variable into all other equations and simplify.
We will derive an objective function and a series of constraints from the following problem. A train producer makes two types of trains, steam trains and fast trains. The production of the fast trains and steam trains requires three operations: steelwork, welding, and finishing. Manufacturing a steam train requires 3 hours of steelwork, 9 hours of welding, and 2 hours of finishing. Manufacturing a fast train requires 2 hours of steelwork, 4 hours of welding, and 10 hours of finishing. The factory has allocated at most 66 labour hours for steelwork, 180 labour hours for welding, and 200 labour hours for finishing. The profit per steam train is $90, and the profit for fast train is $75. How many steam trains and how many fast trains should be produced each day to maximise the profit? Steel, 3 hours per steam train plus 2 hours per fast train is less than or equal to 66 hours in total. Welding, 9 hours per steam train plus 4 hours per fast train is less than or equal to 180 hours. Finishing, 2 hours per steam train plus 10 hours of finishing per fast train, less than or equal to 200. We need to maximise Z, the objective function, or profit, i.e. 90 for steam trains and 75 for fast trains. X is the variable used to represent steam trains and Y is the variable used to represent fast trains. We also know that we cannot produce a negative number of trains, so both X and Y are greater than or equal to 0. The equations are already in standard form as they have the properties described above. We now convert to slack form. We introduce slack variables x2, x3, and x4, which are assumed to be non-negative, and so we constrain them to be greater than or equal to 0. We rewrite the equation as follows, such that now the slack variables measure the tightness of the constraint. We now perform a pivot operation on any non-basic variable with a positive coefficient in the objective function. Here, I choose x. We find the equation with the tightest constraint on that variable, which is equation 3. We can only increase the x value here to 20 until we break the non-negativity constraint of x3. We now pivot and replace x with x3.
After substitution into all other equations, we arrive at the following set of equations. We now repeat the process with y as it has a positive coefficient in the objective function, and find that equation 2 is the tightest when one can set y to 9. Before breaking any constraint, we pivot and swap y with x2 and substitute. We now choose x3 from the objective function and find its tightest constraint. If we repeat the same process, we find equation 4 is the tightest with a maximum of 18. We swap x3 and x4 in a pivot operation and simplify. We arrive at the following set of equations. We can now see that all non-basic variables in the objective function have negative coefficients, meaning that it cannot be maximized further. This means that Simplex terminates with an objective value of 2,250. If we set non-basic variables x2, x and x4 to 0, we arrive at the solution with x equal to 10 and y equal to 18. Graphically, Simplex initially started at the origin 0, 0 and moved to 20, 0 when we first set x to 20. We then moved the vertex to the vertex at 69 where we increased y to 9. We finally increased the objective function to 2,250 at 10, 18.
Computational complexity. The algorithm has an exponential worst-case runtime for a family of linear equations, shown by Klee and Minty in 1972. However, the algorithm is very efficient in practice, having an average complexity of polynomial time. It is an open question if there is a variation with polynomial time or even sub-exponential worst-case complexity.